Welcome to the channel. Today we are going to be doing an intro to reinforcement learning. So let's start with just a little bit about what reinforcement learning is and why you might want to learn it. So reinforcement learning is any algorithm where you are interacting with an environment and getting reinforcement, a reward, from that environment that teaches you how to interact with it more effectively. So in practice, this usually means you have an agent, maybe it's playing a game. You're not giving it the rules to the game. You're not teaching it anything about the game. You are simply giving it the points based on the game. You're telling it when it did well, and you are giving it that reward. And then the agent, the entity interacting with that game, is going to learn from that reward and try to get better at playing. That is at core what reinforcement learning is. So what are you going to get out of this video? Well, we're going to cover very briefly some of the theory behind reinforcement learning, how it works. We are going to walk through some of the tools that I use to build these agents. And really, I'm going to try to set you up with a framework as a beginner that you can start to use to explore other environments, make changes, and build on. That's a lot of my goal today, is to give you sort of a framework and code base and tools that you can take forward and work with, and actually, start to work with these projects. This will not be a full course. You cannot shove a full course on RL into a few hours of video here, or whatever this ends up being. I'll provide some links and some recommendations towards the end of the video to sort of go and start to build your knowledge out from the ground up. So, super quick intro to RL, tools and technologies you'll need, and then we will jump in and we're actually going to start coding out the agent that will play Pong with Q-learning. So let's start off with how RL works. So we have an agent here, and the agent is your actual, Q-learning function here, your agent that's interacting with our environment. So we have an agent. It's going to take an action on an environment. So in the context of Pong, that action could be move paddle left or move paddle right. The environment is then going to return a reward, the next state, often also called next observation, info, and done. The reward is kind of self-explanatory. That's going to be a number. Either you scored or you lost a life. In other words, the other player scored. The next state is going to be, in this case, a picture of the environment. So we're going to be learning from pure pixels. It's going to return an actual photograph of what's going on in the game for the agent. An info dictionary, which is going to return some info about the environment, things like number of lives, level, and such. And then done is going to be a true or false value, telling you whether or not we are done with that particular round. Did the game finish? The agent is then going to take that information, the action that it just took, the state that it was in, along with reward, next state, and done, and it's going to pass it to the buffer. So Q-learning is usually considered an off-policy algorithm. That means that the training occurs off of the policy. It's not part of this core loop. It is off in sort of a separate process. So we're going to store all these things into a buffer. That buffer is going to be quite large. This can be 500,000 images, 1 million images. This will take a fairly large amount of memory on your computer, which is probably a good time to say that you probably do want to go into this with a fairly hefty machine. You want a decent GPU to train these things quickly. You want a decent amount of RAM to be able to store your buffer. Any good gaming PC should do. A gaming laptop might do it for you. And if not, there are services like RunPod that you can use to train models remotely and use someone else's GPU. So just sidebar there. You will need a little bit of horsepower to do this. If you're trying to do this on a quad-core budget laptop with no GPU, you are probably not going to have very much fun working through this tutorial. So we store all these things in a buffer. That buffer is going to store all of these experiences: state, action, reward, next state, done. And then the training loop is going to pull batches of data from the buffer and attempt to update the model and then update the agent. So the model, and really, I've got these as two separate boxes for illustration. Really, the agent has the training loop in it in this scenario, but for sort of our mapping, here, I'm setting them up as separate things. So you've got your training loop pulling from the buffer, updating the Q values, which then lets the agent take better actions on the environment, which then returns different rewards, and then the cycle continues. So let's talk about, you've heard me mention Q learning a couple of times. Let's talk about what that is. So Q learning is taking the value of an action. So you'll often see that as Q S of A, something like this in equation format. Q S of A. And what we're looking for is the value of an action in a given state. So let's use this grid to kind of talk through this. So let's say the reward down here is 10. So this is our target. This is our start. This is our target. Well, we want our agent to be smart enough, and let's assume you can't go diagonally. We want our agent to be smart enough to find, this reward successfully. Well, let's say that every time it takes a step, we have a penalty. So let's have our hypothetical agent. It's starting at start. It's going to 1. Hey, no reward here. This is now a -1. Hey, go into the next box. No reward here. This is a -1. Maybe it wanders off. All right. It didn't make it anywhere. It stopped. Now it starts again. It goes down here. It says, well, going left, going right has a value. Again, this is sort of your classic, Q value table approach. So going right has a value of -1. So we shouldn't go right. We should try going down. That doesn't have a negative value. So we tried going down, no rewards there. We tried going over, no rewards. We're going to keep going. We're going to keep trying things. We go over here, and we still have a negative reward. But then, hey, we hit 10. We hit our reward. So what this approach would do is it would say, hey, you just fed in a state, action, reward, next state, done. So what that buffer would tell us is that from here, from this state with a reward value of -1, the next state has a reward value of 10. All right, so what would it do in the training process? It would come back and go, hey, maybe if this is a reward value of 10, maybe the real reward value here, the real value of this state, and specifically this state with this as a next action, is 9. So it would then go through the next training pass. So it would, really, it would probably wander up here a little bit. You'd see lots of wandering, lots of trying things. But what you would ultimately end up with is you would end up with it starting to fill out a table that looks like this. So if this is a 9, then these two are 8s. And these are 7s. And this is a 6. So what that starts to tell us is as our agent is looking around at the best way to get to the final reward of 10, it now has a value approximation, a map in this table that tells it that we have a reward along the way. We have a value of that next state that approximates what this value is worth. So it knows, hey, I'm starting at start. I'm not going to go up because that only has a value of 1. I'm going to pick either down or to the right. So I'm going to pick a value of 6, then 7, then 8, then 9, and then, hey, I made it to my final reward here, which was 10. So this is really simplistic, but this kind of gives you a little bit of a view of what's going on behind the scenes. What the model is doing in all this is the model is approximating that value. So it's basically, we're feeding in in Pong, it's not like it's a table. It's not a basic numerical chart that you can pass in. You're feeding in an image. You're saying, hey, here's a paddle and a ball and, the rest of the game setup. That's a fairly complex thing to say, hey, yes, this particular array of pixels has this state value. But that's what the model's there to approximate. It's there to approximate the state based on the information passed into it and the rewards that we've given it over time. So it's kind of what we're going to be building here. This is an article I will link that kind of covers the same approach that we just talked about with slightly prettier diagrams. Here is the action value function. You're going to see this a lot in other RL courses. That's Q of S of A. So the value, really, all this is doing. So Q of S of A is the Q value of this state active action pair with the sum of all, basically all future rewards. So again, it's trying to, when we say sum of all future rewards, it's trying to value this with the 10 in mind. It's trying to say, hey, we're not just looking at the value of this square, because really the value of this square is nothing. We're looking at the value of this square. So we're looking at this valued as the sum of all future rewards. That's what this is saying. When state is state and action is action. So you're going to see that more. Don't get bogged down in the math. We're not going to use a whole lot more of it. Let's go ahead and jump in and talk about the tools you're going to need. So PyTorch is the library we're going to be using. The two big ones are PyTorch and TensorFlow. I use PyTorch for most of my projects. I think TensorFlow is a little bit more is a little bit more used in business. PyTorch seems to be a little bit more used by researchers. I've built most of my stuff in PyTorch. That's what we'll be using today. This little graph here is important. So, or not graph, but selector. So what you want to do here is you want to obviously choose stable, pick the operating system you're using. So I'm using, Linux. You might be using Windows or Mac. You want the package type. This should be pip. We are going to use Anaconda, but for the way I'm going to do this, we're going to use pip. You're going to want Python, and then you are going to want the CUDA version for your graphics card, and that is something you will want to look up. For me, it is CUDA 11.8, but if you're using a different NVIDIA graphics card, this might be different for you. So look that up, get the command, don't run it yet. The next thing we're going to have in play here is the environment. So this is, I guess we haven't really talked about environments yet. So OpenAI gives us this really cool tool called Gym. And OpenAI Gym is basically a pre-made environment that you can use to train reinforcement learning agents or other autonomous agents. It's going to, already be set up for an agent to interact with. It's already going to return the right information, reward info, all that good stuff. Basically, this is just a prepackaged, easy way for you to start working with, reinforcement learning algorithms. You can absolutely write your own environments. I actually cover that in other videos, but this is the best way to get up and running very, very quickly. I chose Pong just because, one, it's kind of a classic game in the RL space, and it's a relatively simple thing to get started with. Again, this was sort of focused on beginners, but you can actually go through once we get this working, and you can play with other environments and try to get these other environments working. I am going to be using Visual Studio Code, VS Code. You do not have to use my preferred editor. You can use whatever editor you want to. I'm going to be using some plugins, really just the TensorBoard plugin and the Python plugin to work through this series. But you can use anything you want. If you're already comfortable programming and you have your own IDE and you don't mind going and launching TensorBoard separately, use whatever you're comfortable with. This is what I'm going to be using, and I will drop links to all of this down in the video description. TensorBoard is something we are going to be using to visualize our agent's progress. So reinforcement learning can take a long time. This could take, an hour to see any kind of good results. It could take, 10, 12 hours or more to get, to the level that you want it to be what you might consider fully trained. There are some projects that I have that will take multiple days. So visualization is really, really important. In some of my early videos, I think I just used matplotlib and I had it print out, pictures to the workspace. TensorBoard is much, much easier and is going to give you some more live tools to sort of reshape the data and look at it a little bit more effectively. And then finally, I'm going to be using Anaconda to manage my Python environments. The only thing we're going to be using this for is for a virtual environment. So if you don't know what virtual environments are, in Python, you have the ability to spin up multiple environments on your computer that have different library versions and keep those things separate. Over time, if you're just starting out, you just installed Python, which that's probably a good point. You actually do need to go download Python. I don't have that up as a link right now, but you do need Python in your machine. But if you just downloaded Python, you have no idea what you're doing, and you don't care about breaking other things or other projects because you don't have other projects, then you may not need something like Anaconda. Anaconda is going to be something that lets you download and work with multiple environments. So if I need Python 3.10 or Python 3.11 or 3.12 for a specific project, and I need them to have certain versions of certain tools, Anaconda gives me the ability to go and say, hey, I want this specific version for this specific environment, and then I want to use that over here in VS Code. So I do recommend downloading it. So let's talk about immediate steps for you to take. And again, all links in the video description. Go ahead and install Anaconda. You do not need to install TensorBoard if you're using VS Code. If you are going to use VS Code, go ahead and install this. And then wait on PyTorch. We're going to get into that with into the code. So Anaconda, VS Code, and then pause. So I am going to pause for a moment and grab some coffee, and I assume that when I come back, you will have downloaded and installed the tools. All right, so I'm going to assume that you have, your Anaconda is up and running. You have VS Code. If you're going to have VS Code or you're comfortable with something else, let's go ahead and start putting this project together. So I am going to run a command called conda create, and it's going to create an environment called rl-4-beginners, and that's actually what I already built, so I'm just going to call this one lesson. You can call this whatever you'd like. It's just necessary to give it a name. And I'm going to call it with Python 3.11. All right, so it's asking me if I want to proceed. Yes, I do. All right, I'm up and running. And I'm going to, in my own lessons directory here, I'm going to create an rl-4-beginners folder. You can put this anywhere. And if you're using VS Code, you can literally just launch this with code dot. Very simple. All right, so I'm going to be using just a little bit of housekeeping here. I'm going to go ahead and set up a .getignore because I'm going to be using Git to track our files over time here. And I will check this entire repository in for you at the end. But I do not recommend waiting. I recommend coding along with me. So in our getignore, we are going to go ahead and ignore runs, models, and star.pyc. Those are PyCache files. We don't want them. I'm also going to set up a VS Code tasks.json. And this is not really necessary, but it does make things easier. And I've got a whole video on automating things with tasks.json that I will link in the video description if you want to use this approach. All this does for me, and this I'm going to copy in. I will copy in almost nothing else. So all this does for me is it's going to call a train.py file when I hit a keyboard combo. So in this case, I can hit Control-Shift-B, and it's going to try to call train.py. You can also just do this with, when you open up a py file, you'll see a little green run button. That's also perfectly acceptable to do. I find it to be a little bit slow to have to reach from a mouse, so I use a tasks.json. So again, if you want to pause and copy this, you're more than welcome to. If you want to go watch my other video on automating your workflow, I will link that in the description. All right, so we've got some of the sort of housekeeping VS Code stuff out of the way. Oh, let's talk extensions. So you are going to need the TensorBoard extension, launch and view TensorBoards with VS Code, and you are going to want the Python extension down here, Python language support. And actually, I think, okay, I do not have the extension pack. I just have the Python extension. So go get the Python extension, get the TensorBoard extension. Those are going to be necessary as we move forward. All right, so let's go ahead and start pulling in our requirements. So I'm going to create a requirements.txt. And if you recall, a lot of what I promised was that I'm going to help you build a framework for building these things. Everything I'm typing out now is part of that framework. You want an easy way to fire off your code. You want a clean getignore. If you haven't used Git, it's a version tracking system. You should definitely go look that up. But this is going to be useful to not check in the things that you don't want to check in. A requirements.txt is important. A lot of for beginners tutorials are going to have you just install Python and then start pip installing things. That's great, except you can't recreate your environment. If you just ran through and pip installed things, then if you're coming back to your environment a year from now, you don't know what was in use. You don't know what you were, what you were actually using to build that environment. So let's go ahead and get started filling this out. So we are going to need a few different packages. We're going to need Gymnasium, and that's going to let us pull in our, we'll do Atari, and that's going to be 1.0.0. That's going to let us pull in our Pong game. We're going to need ALE-Py because this is an ALE environment, 0.10.2. We're going to need TensorBoard. This is why you didn't have to install TensorBoard, because it is a pip package, 2.19.0. We're going to need OpenCV-Python, 4.11.0.86, and we're going to need Pygame. All right, and then we get to the Torch installation. This is going to be a little bit specific to your computer. So coming back over to this start locally side. So you're going to see pip3 install Torch, Torch Vision, Torch Audio, and then you're going to see an index URL. So I'm going to ask you not to just run this directly, but to kind of chop it up a little bit. So what you can do, you're going to copy this, and you're going to change it to --extra--index-URL. And what this will do is it's going to make sure that anything in your requirements.txt that's after this URL will get pulled in from this pip URL. There's a few different ways to do this, but this is the best way I found to include packages from multiple different sources. So everything else you just want to pull back for your normal Python repositories. PyTorch here, you want to pull from this repository that will give you CUDA support. And if I didn't say that earlier, that is kind of a critical piece here. So CUDA support is going to allow you to use your GPU in training, and specifically an NVIDIA GPU. So if you don't enable with CUDA support, what you're going to find is these things just train on your CPU, and they are going to train very, very slowly, which is not great. You don't want that. All right. So we've got our Torch. Now I'm going to open a terminal, and you'll notice here that says ROS2. That's not what we want. We are not in the correct environment. So if you're in VS Code, you're going to do Control-Shift-P and start typing Python : select interpreter, and then it should auto discover your interpreters. You'll notice I have a bunch of Anaconda interpreters here. If it doesn't auto discover, you can enter the path and have it route to a specific interpreter. But in this case, I am going to, for beginners, lesson. And now, if I close this out and do a new terminal, you'll notice over here it says RL for beginners lesson. All right, so now I'm in the right environment. I'm going to do a pip install -r requirements.txt. And it's a requirements.txt by convention. There's nothing magical about that file name. I could have made it rec.txt or anything and passed it into that command, and it would have taken it and gone and loaded things in our environment here. All right, and it's going to think about that for a minute. So let's go ahead and start coding out I think we're going to go ahead and start with the buffer. So kind of coming back to our draw.io here, we're going to build this component, the piece that actually stores all of the data as it's entered. And this is kind of continued boilerplate code. By the way, if you see this error, pips dependency resolver does not currently take into account all packages. That is not an actual, that's not a blocking error. That's fine, at least in this context. So let's go ahead and we're going to create a buffer.py. And this buffer is going to have it's going to have about 6 different blocks of NumPy arrays. So let's go ahead and start with our imports. So we're going to import NumPy as NP. And actually, we did not include NumPy. I think NumPy is included by default in some of these other packages, but let's just go ahead and include it explicitly. Let's make sure we've got it. Okay. And then we're going to import Torch, which is PyTorch. And then our class is going to be replay buffer. And we are going to init. And the arguments for our init method are going to be max underscore size, input underscore shape, and actions for the number of actions, and device is equal to CPU. So why am I saying device CPU? Well, you've got a little bit of an interesting situation here with memory on your machine. So you've got two. This is probably something we should talk about. So you've basically got two blocks of memory that are going to matter. You've got your standard computer memory, which is your CPU, and then obviously you've got your GPU. Cool. Your GPU probably has a limited amount of memory. If you're running, say, a 3060, I think you've got 8 gigs of RAM on that thing. If you are using, your regular desktop, maybe your regular memory has 24 gigs available. RAM sticks are cheap. GPU memory is not, in general. It is relatively easy to load up your computer with a lot of RAM. Versus if you want a large amount of memory on a GPU, you're probably spending a lot of money. So what you want to do is you want to load the important things onto your GPU memory. So as we talk, if we come up to our diagram here, our top diagram, this buffer is going to hang out on CPU memory because this is going to be, 1 million images. And actually slightly more because we're going to include state and next state. So it's actually going to be 2 million images. So we want those 2 million images to be stored on your computer's regular memory. And I'm saying CPU here because in PyTorch nomenclature, it's that we're sending it to the CPU. But just think of this as your normal, your RAM on your machine. When we get to the training loop, this is going to take that data and it's going to push it to the GPU. So we're going to pull in a batch of, say, 64, state action pairs. We're going to push it to the GPU, do our training, and then come back and continue on with execution on the CPU and with CPU memory. So coming back to our code, that means that we really want the CPU here to be our primary method of storing data. And when we get to the sampling side of that, we're going to send data to the GPU. And actually, looking at my code, we may handle the CPU part automatically, and this may actually be a GPU. Anyway, we'll get to that as we get into the code. So we're going to say self.mem size is equal to max size. And this does allocate all of the memory right off the bat. So if you're going to run into a memory issue, you'll find out as soon as you run the code. Self.memctr is equal to 0. Self.state memory is equal to np.zeros. So what we're doing here is we're basically pre-filling the memory buffer with zeros. It's a lot more efficient to do it this way. We're just sort of pre-allocating instead of every single time we add a record, extending the memory. That would be very inefficient. This is a relatively efficient way to do this. So we're going to say np.zeros, and that is going to be of size self.memSize, and then an expanded star input shape, and then we're going to say dtype is equal to np.uint8. All right. We're just going to copy and paste that. And this is going to be next state memory. And next state memory is going to be self dot, it's going to be the same, basically, no change. Let's see. So that should be fine. We're going to do action memory. So self.action memory is equal to np.zeros. Self.memSize. And dtype is equal to np.float32. All right, and action memory here. So why do we not have a double set of parens or parentheses? Well, for state memory, this is actually a multi-dimensional array. For action memory, this is just, you know, of size, mem size. It's just a single dimensional action. So really, we should be able to also do this one as uint8. Self.reward memory is equal to np.zeros self.memSize. Dtype equals np.uint8. And then finally, self.terminal memory is equal to np.zeros self.memSize. Dtype is bool. And self.device is equal to device. All right, and then you'll notice we never used nActions. That was left over from another implementation, and I copy pasted it into this one, so you can actually remove that. You do not need it. All right. Next, we are going to define whether or not we can sample. So something you want to be aware of is you don't want to sample a buffer that's too small. If you've only passed through, one, you need it to be bigger than your batch size. So if your batch size is 32 and you've only run through 3 steps, well, it's going to crash if you try to sample 32 from it. But even once you've got sort of your minimum batch size, you actually want to let that grow a little bit more. Otherwise, the model can overfit to a very small amount of data, and it can do that very quickly. So we want to go ahead and basically say, we want to have a method that says, hey, am I allowed to sample yet? Can I have data? So we're going to say def can sample self and batch size, and we're going to say if self.memCounter is greater than batch size, and I'm going to do times 5. So whatever my batch size is, I want 5 times batch size before we try to do any training. And if that is true, then return true, else return false. Okay. So let's store a transition, and then the memCounter part will start to make a little bit more sense, I think. So we're going to do def store transition self self state action reward next state done. Again, coming back to our diagram here, we're building this portion. So store transition is what allows your agent to store things in your buffer. So here we're going to say index is equal to self.memCounter. We're using the percent or modulo operator, and self.memSize. So what are we doing here? Let's talk it out for a moment before we continue. So if our memory size is 10, let's say memctr is, our mem size is 10. All right. Then if our index is 5, so, or if we let's say our mem counter is 5. So mem counter CTR is 5. That basically means that we've stored 5 things. We have counted up to 5 in our memory buffer. Then we're going to store things in number 5. If somebody passes in, a series of records, those will get stored in an index of 5, because that's what we're doing. We're saying the modulo operator, it's a remainder operator, basically. So we're saying, 5 divided by 10 modulo, let's see, 5 modulo 10 is going to equal 5, basically. 5 divided by 10 is going to have a remainder of 5. All right. But what if mem counter was 11? Well, now 5 modulo 11 modulo 10 is going to have a remainder of 1. You're going to end up back at counter 1. So what this ends up doing is it ends up filling up the buffer. So your mem counter is right in sync until the buffer's full. And then it effectively goes back to the beginning of the buffer and starts overriding the oldest experiences. So why would we do that? Well, one is we don't have infinite memory. You probably can't hold millions and millions of experiences on your computer, even though it will take millions of screenshots and experiences as we go through this process. So you want to keep a fairly large buffer. You can't just let it go on forever. Doing this method basically lets you pre-allocate all of your memory and keep, continually refresh your data in a very efficient way. So that's what we're doing. That is why index is set up the way it is. So let's delete all that. We're going to go ahead and say self.state memory index is equal to state. Self.next state memory index is equal to next state. Self.action memory index is equal to action. Actually, not quite. It's going to be equal to torch.tensor action.detach.cpu. And I'm going to be very honest and say I don't remember why I had to do this, but it was important. Self.reward memory index equals reward. Self.terminal memory index equals done. And then, of course, we are going to increment self.mem counter plus equals 1. All right. Now let's get into our sample buffer. So we're going to say def sample buffer self batch size. We're going to look for the max mem. So what is the maximum? And you might ask, well, why wouldn't it just be mem size? Well, mem size may not be full. We want to pull from the area of memory that is currently full. So we're going to say max mem is equal to the min of self.memCounter and self.mem size. And then we're going to pull a batch using np.random.choice. So that's NumPy taking a random choice of values of size, batch size, up to max mem. So at this point, this is just going to be a bunch of numbers. This is not actually a batch. This is more of the batch indices. So then we're going to say states is equal to self.stateMemory batch next states is equal to self.stateMemory batch. Actions is equal to self.actionMemory batch. Rewards is equal to self.rewardMemory batch. And dones is equal to self.terminalMemory batch. All right, and then for all of these, we're going to go ahead and convert them to a tensor in float32, and then we're going to send them to device, which in this case will be your GPU by the time we run this. So we're going to say states equals torch.tensor. States dtype is torch.float32.to self.device. And then just copy this. We're going to do it a few different times. So this is going to be next states. This is going to be actions. This is going to be rewards. And this is going to be dones. All right, and the only one we should have to change the data type for is down here. This is going to be torch.bool. So this is making sure that we are storing, we're basically taking in all of this information and we are storing it, or we're bringing it back on the GPU. So store transition, we're not doing anything. We're just, letting it go through the CPU. This one we are sending to device GPU. All right, and then finally we can say return states, actions, rewards, next states, and dones. All right, and that completes our buffer.py. So next up, I'm going to pause for a moment, and then we will move on and probably start working on our model. All right, so we are going to go ahead and create a model.py. And in model.py, let's just kind of sketch out what we're going to be doing. So we are going to have two sets of layers. We are going to have our convolutional, so CNN layers. And we are going to have our fully connected layers. And I am not going to go super in depth on how these work. Convolutional neural networks are a whole course and topic to themselves. I will recommend some courses at the end of this video that will cover a little bit more information on and really go in depth on how CNNs work and help you get used to them. For now, what I want you to take away is that the convolutional net, the CNN, is going to be, which CNN stands for convolutional neural network. The convolutional net is here to recognize the image. So this is going to recognize image, and it's going to pull features out of the image. So what convolutional neural nets do let me see if I can pull up a quick diagram. Neural network diagram. All right. This is probably a good way to start. So convolutional neural networks basically take a kernel. They take you can think of it as a little square that reads over the image, and they're going to read, across the image. It's going to grab all these little squares of data. It's going to feed them through a series of convolutional layers, and as it feeds through, it's going to create these layers of data. It's going to create, it's going to extract features from the data. When we finally get to the end, we're going to have, instead of a big image with, nothing that the model can really understand, we're going to have a series of features. And then those features are going to get flattened into an input layer. That input layer is going to get passed into the fully connected layer, which is what actually makes does the processing and the calculation to determine what to do next. So in this diagram that I just pulled up, it's doing a classification. It's saying, horse, zebra, dog. For our model, it really is the same process. It's going to take an image. It's going to take an image of a Pong screen, and it's going to output, instead of whether it's what it is, it's not classifying. It's going to output a direction. So it's going to say, hey, based on this image, move paddle left, move paddle right. That's basically what our network is going to try to do. So you can think of it as those two layers. We're going to build the image classification portion, and then we're going to build the portion that actually, takes that image information and does something with it. We are also going to be building in some methods that will save and load the model. And you could do this external to the model class. I would just rather have it be, self-contained in that way. So this is going to be a little bit of a longer one, but let's go ahead and get started. So we're going to import torch, import torch.nn as nn, import torch.nn.functional as f, and then we can go ahead and say class model, and we are going to inherit from nn.module. So we're basically inheriting from the PyTorch nn module class. And then let's go ahead and do init. And VS Code autofilled a little bit more for me than it needed to. We're going to take in an action dim, hidden dim. And the hidden dimension is basically those middle layers of the network. So we're going to say that's 256 neurons. And observation shape, we're going to default to none. For super, and super in Python, of course, is just calling the base class and running it. So we're going to pass in model and self to init. All right. So first, we're going to do our convolutional layers. So self.conv1 is equal to nn.conv2d. We're going to say in channels 1, out channels 8, kernel size is 4, and stride is 2. So kind of going back to our, I closed that diagram. Let me pull it back up. So going back to our diagram for just a moment. So you can think of the channels as the features that we're trying to extract, number of features. It's a little blunt, but it'll work. Kernel size is the size of this square that's getting, layered over the image. The stride is how much of a hop the square is taking. So you generally want stride to be less than kernel size. So, if it's a 4 pixel, kernel, it's going to move over by 2s. So it's going to have some overlap as it slides across the screen. Yeah, that kind of gives you an idea of what we're doing. The number of layers is not arbitrary. It has to do with the image size passed in. So we are going to be using 3 because we're going to crunch the image down into a 64 by 64 image before we even send it into this process. So let's go ahead and copy this. And we're going to call the second one conv2. And here we're going to have in channels 8 out channels 16. So your channels should increase. And we'll leave kernel and stride the same there. And then we'll do conv3. And we're going to do in channels 16, out channels 32. And here we're going to lower our kernel size just a little bit. So every time you go through one of these layers, the image effectively gets smaller. So if I passed in 10 layers, or honestly, maybe even 4 layers, we would end up with an error saying that, you know, your image size can't be less than your stride size. Basically, we would have compressed the image too small for this to actually continue doing feature extraction. So your number of layers will really come down to your output. 64 by 64 is pretty good for most of these Atari games. And if you're wondering how to determine that, a good way to look at it is to actually get a printout of what that image size looks like for a particular game, and see if you as a human could play it in that size. And I don't mean could you physically see it. I mean, if you blew it up a little bit, would you have enough details to play the game? So Pong is pretty simple. It's a couple of paddles, a ball, and a screen. So as long as it has enough pixels to make out those paddles, then you probably have enough data to play. If you're doing something more complicated, then maybe you do need all of your pixels and all of your data to be able to play that game and get the information you're looking for. But for this, it's three layers, and that is enough. Now, before we go on, I'm going to define a helper function called calculate conv output. And this goes back to giving you a framework. So it is very possible. So that what comes out of these is going to be, a layer based on the size based on the convolution, layers that you fed in, and the image size that you started with. So it is actually variable from project to project depending on the image size. Now you can sit down and mathematically figure out, and it's not that hard, but you can mathematically figure out how big that output is going to be. But it's not declared. It's not like here where I know out channel 16 should be in channel 16 here. You have to either mathematically figure it out or run the code and see an error and then fix it. What I've put together here is a really simple little function that is going to return the correct output shape so that we can feed it into the next layer. And I found this just really helps me as I'm using CNNs across different projects. So this will only ever be called once when the model starts, but zeros, we're going to do torch.zeros of star observation shape. And then we're basically just going to pass it through our model f.relu. And this will mimic what we're going to do later on. conv1 x, and then you're just going to copy and paste and pass it through conv2 and conv3. And then we're going to return x.view -1 dot shape. And what that should give us is we should be able to do conv output size is equal to self dot calculate conv output observation shape. I like to go ahead and print out some data here. So we're going to print conv output size and conv output size. All right. Finally, we will define our fully connected layer. So we're going to do self fc1 is nn.linear of conv output size. That's where we needed this. So if you think about it, the data is going to flow in through these. It's going to come out as a flattened layer. We'll get to the flattening soon. and then it's going to feed in to the conv output, the fully connected layer at size conv output size, hidden dim. All right, and just like above, here you're trying to match the number of channels. So out channels for layer 1 must be in channels for layer 2. For the fully connected layers, you are trying to match the sizes. So the size here, the output size of the first fully connected layer should match the input size of the second fully connected layer. So in this case, this is going to be hidden dim on the way in and also a hidden dim on the way out. Self.fc3 will be same, hidden dim, and then self.output is equal to nn.linear hidden dim and action dim. So output is actually going to take the is going to take the final weights of your hidden layer. It's going to pipe it into your actual action dimension, which is going to be 6 or 7, I think, for this particular environment. So that's the actual number of outputs that this thing could have. And then we actually need to do a weights initialization. And I'm going to say to do there. We will need to define one more function before we can do this. So we'll come back and do weights in a moment. Let's go ahead and get our forward method in. So we're going to do def forward self and x. So what is the forward method? The forward method is what actually gets called when you call your model. So all this was initialization. This was just setting up the model. The forward method is what, when you say model and you pass in data, it's going to call forward, and then that is going to return the results. So this is where the actual magic is happening here. So first thing we're going to do is we are actually going to divide x equals x divided by 255. So why 255? Well, your image value could have up to 200. Your image value or your image color value could be between 1 and 255. At the end of the day, these models are just matrix multiplication. I mean, there's definitely more to it than that. I am super oversimplifying, but it's just math. It's a matrix getting passed through a network. If you supersize the input, if one input is a 1 and another input is 243, then there's a possibility of the 243 input overpowering the other inputs, even though it's not actually more important. So what this does is it normalizes it, and it's going to shrink all values to between 0 and 1. We know the max value is 255. Dividing by 255 gets it all between 0 and 1. And that is very, very important for model stability. So next, we are actually going to copy these because it is the exact same content. That was the whole point. We're going to do x equals x.view, x.size, and view lets us reshape. I know it sounds weird, but that is what view is doing for us here. And then we're going to pass into our fully connected layers. So x equals f.relu. Your relu is your rectified linear unit. That is adding a non-linearity to the network. So self.fc1, x. All right. And we're just going to do self.copy that a couple of times and do self.fc2 and fc3. And output is self.output. And then return output. And that is basically the entire forward method. This is what gets called when you execute your model. So we're passing, we're taking an X, we're taking an input, we're normalizing it, we're passing it through our convolutional layers and extracting some image information. And then we're passing it through our fully connected layers and extracting some information, what action needs to be taken through the fully connected layers. And then finally, the actual self.output is the action, and we're returning output. All right, now we need some helper functions. So we are going to define a weights init. This is one that I wouldn't worry too much about. You can go Google chiming weights initialization and Xavier weights initialization. Basically, what we're trying to do is set a fairly regular distribution of initial weights out of the box. When you just go create a model, it's going to be completely random. You can have some things that are super heavily weighted, some things that are not, and that can steer training in the wrong direction at first. So we just want to go ahead and do a weights initialization of our own. So we're going to say def weights init. We're going to say self and m for the layer. If is instance m of nn.conv2d. Then we're going to say nn.init.chiming normal m.weight. Nonlinearity is ReLU. If m.bias is not none, nn.init.constant m.bias 0. All right, and then we'll do elif is instance m nn.linear. Oh, not L1 loss, linear. Then we're going to do nn.init.xavier normal. That's Xavier with an X and it ends with an underscore. m.weight. If m.bias is not none, then nn.init.constant m.bias and 0. All right, and then we can come back up here to our to-do, our initialize weights to-do. And in our initialize weights, we can do self.apply, self.weightsinit, and we have done our weights initialization. All right, we're almost done. We need to add some additional helper functions in here. We are going to do def save the model. And you could do this external to the model. Again, I just like to have everything kind of wrapped up in one class so that you're not treating the model as a data type, you're treating the model as an object. You can just tell the model to save or load itself. So we're going to say self file name equals models/latest.pt. And then we're just going to do torch.save self.stateDict and file name and def load the model, self file name, same deal, models/latest.pt. So you might be asking, why even make it a parameter? Why not just hard code it? Well, if you're, a lot of reinforcement learning requires experimentation. This, we're probably just going to go with latest, but maybe you want to run 5 different training runs at the same time with different inputs, and you want to save those that model training information in different files, or your state for those models in different files. Or maybe you want to do a save that is hey, it's been 1,000 iterations, I'm going to save. It's been 2,000 iterations, I'm going to save. I've had training scenarios where something, maybe it ran and went up for 3,000, and then it tanked for some reason. And I wanted to grab, an output, a save point from, every 1,000 or so I could try to understand what was it doing right before it started doing badly, and then what was it doing right after. So you do want a little bit of variability here. So we're going to, for load the model, we're going to try self.loadStateDict. And the reason we're doing this as a try is we don't want the code to fail if it's not there. Or maybe you do. I don't in this scenario. So I'm going to say printf loaded weights from file name. Except file not found error. And we're going to say print f no weights file found at file name. All right, and then we should be done with our model class here. Let's go ahead and bounce over and start working on our agent. And this is where we're going to start tying some of these things together. So the agent is going to be agent.py. And we're going to need a few different things here. So we're going to go ahead and you know what? I think I missed two different helper functions on this model.py file. So this will be outside of the model class. We're going to need a soft update function and a hard update function. This will allow us to copy model weights from one to the other, and I'll explain a little bit more as we go. So we're going to do def soft update. Let me see if I'm using both. Okay, we're only going to need soft update. This is that's the hazard of copying code from one code base to the other, is you do end up with certain things that were maybe unnecessary. So in this scenario, we do need soft update. So we're going to need target, source, and tau. So we'll talk a little bit more about this soon. But when you're training, you want certain things to provide some stability. So we're going to have two models. We're going to have, a primary and then a target model. And one of those models will kind of follow another or follow the other. It'll lag behind it a little bit. And the way we allow it to lag behind it is with this soft update function. So we're going to say for target param in zip target.parameters source.parameters, and then target param.data.copy and target param.data, and type it with me, and then I'll explain it a little bit. 1.0 minus tau plus param.data times tau. All right, so what we just did here, so let's think about what this would actually do. So tau is a very small number. It's 0.0.5. So 1 minus tau is going to be the, a very, a relatively large number, right? 1 minus tau. If target param.data was 2, then, or we'll keep it between 1 and 0. We'll just say it's 1. So target param is 1 minus tau. Then it's literally going to be 0.0 995. The param.data times tau is going to be a very small number. So what this little function ends up doing is slowly inching the target towards the source. So it's going to keep most of the data of the target, but it's going to add a little bit. It's going to kind of average in a little bit of the data from the source. So it's going to, that's why it's called a soft update. We're not fully updating the target to the source. We are just kind of slowly inching it towards the source data. All right, so let's go back to our agent.py, and we are going to come up here to the top and say from buffer. That's the buffer that we set up. We're going to import replay buffer. We're going to say from model, import model, and soft update. We're going to import torch. We're going to import torch.optim as optim. Those are your optimizers. We're going to import torch.nn.functional as f. We're going to import datetime. We're going to import time. And we are going to import, we're going to say from torch.utils.tensorboard, import summary writer. We're going to do import random. Yes, there are a bunch of imports for this one. Import OS and import CV2. All right, we're done with our import marathon here. So let's go ahead and start defining our agent. So our agent is the actual thing that's going to interact with the environment. So we're going to say class agent. We're going to do def init. And this is going to take quite a few parameters. This is going to take an environment, a hidden layer, a learning rate, step repeat, and a gamma value. And we're going to say self.env is equal to env. Self.step repeat is equal to step repeat. We'll talk about this a little bit more later too. Self.gamma is equal to gamma. We're going to go ahead and call an env reset. So when you're working with OpenAI Gym environments, the two things that you're going to work with the most are going to be step and reset. So reset effectively starts the environment. That's going to reset it to its initial state and get it ready to play. Step is actually taking some action on the environment. So we're going to say OBS info equals self.env.reset. And you'll see me use obs or observation and state somewhat interchangeably. The way these are supposed to be used, observation is intended to be what the agent can see in the environment. State implies a full knowledge of the environment. So if you're taking the state from the environment, you know everything about the environment. If you're taking an observation, you're maybe taking a picture of the environment. That's your observation of what you can see. You do not have the full state of your given environment. Now, in practice, people swap both out pretty frequently, but that's how they're intended to be. That is the split and the difference. We're going to do a to-do to call process observation. We'll be defining that function later. Now we need to go ahead and check for our device. So we're going to say self.device equals CUDA 0. So this is your GPU. If torch.CUDA.is available, else CPU. And then let's go ahead and print out, we're going to do F loaded model on device self.device, just so we get some output here. And then now, and apologies for jumping around, but now's probably a good time to go ahead and get a train.py set up so that we can start to, test out these various pieces and functions we're building. So the two files we're going to use are train.py and test.py. We'll mess with test.py later. So for train.py, we are going to go ahead and say from agent, import agent, import gymnasium as gym, and we're going to grab a couple of wrappers here. So what we want to do a couple of things to make it easier for our agent. You can pass in a full-sized, full-color image to an agent, and that's fine. Like, there's nothing at a technical level, there's nothing wrong with that. It is going to take a lot more compute, a lot more processing power, and it's going to take a lot more of your memory because you're storing millions of full-sized, full-scale images. So what we really want to do is we want to grayscale the image, because the agent can learn just as well from gray as it can from a full-colored image. And we also want to go ahead and shrink it down to a 64 by 64 image size, because again, it's enough data for it to learn on while also drastically lowering the computational overhead necessary to do this work. So we're also going to say from gymnasium.wrappers. And this is where I started in the beginning and said that OpenAI Gym is a really good environment to start working with. This is why. They're going to give you some easy things like grayscale observation and resize observation that let you set up your environment and then wrap that environment, to provide these results. So you don't have to do your grayscale image processing. You don't have to do your resizing. You can just use gymnasium wrappers, and it solves it for you. We're going to need a few variables here. We'll define more later. We're going to do hidden underscore layer is equal to 128. Actually, we're going to be quite small. We're going to do learning rate is equal to 0.0001. And we're going to do step repeat is going to be 4. And we will do gamma is equal to 0.99. Okay. We'll add more parameters later, but that should be enough to go ahead and get our agent defined down here and our environments defined. So let's go ahead. Actually, let's talk for a moment about learning rate. So your learning rate is how quickly the agent learns. And you would think just right off the bat that a higher learning rate would be better, right? Except not really. Your learning rate is basically how big of a hop your agent is going to take in response to a stimulus or an instruction. So here's a good way to think about it. If you are trying to tell someone how to shoot a basketball at a hoop, and they're at a 90-degree angle to the hoop, they are pointed just completely sideways. It's to their shoulder, and they shoot, and maybe they're blindfolded. Let's use that analogy. So you're trying to help a blindfolded person hit a basketball or hit a hoop with a basketball, right? So they shoot. The ball, of course, goes completely off to the side. It goes nowhere. Your learning rate is how big of a change you want them to make. So if their learning rate is 180 degrees, then you saying turn left, they're just going to turn all the way left, and now they're pointed in the wrong direction again. They were pointed right, now they're pointed left. They're still missing the hoop. They're still in the completely wrong direction to get anywhere. If their learning rate is that they're going to change by 5 degrees, and you say turn left, well, they're still going to miss, but they're going to get a little closer. You say turn left again, they're going to get 5 degrees closer. They're still going to miss, but they're going to be closer. As you iteratively tell them to turn left and they make very small adjustments, they're eventually pointed at the goal, and they can shoot and hypothetically score. That's the best way I can think of to think about learning rate here. Yes, a larger learning rate will result in bigger swings towards your target, but it can also overshoot your target. It can overshoot where you're trying to go. So for a lot of these things, a very, very small learning rate, like 0.0001, is actually really effective. If you take that out one more zero, if you add a fourth zero in there, you can end up just starting to go nowhere. It is too small of a hop. And this is something that will change from problem to problem. Some problems are fine at 0.001. Some are, require a little bit more specificity. So that's something that you'll get to play with and tweak, and you should definitely try different values here and see what you can optimize. All right, let's come down here, and we're going to say env equals gym.make, and we're going to say ale/pong v5. I've actually broken one of my normal rules because we haven't run the code yet. I usually try to run the code in much smaller blocks. So hopefully this will get us soon to being able to run something. We're going to say render mode is equal to RGB array. And then let's just print out. So we're going to do env, let's see, obs info equals env.reset. We're just going to start here. We're going to start running some code. So I'm going to run train.py with just this. All right. Let's see. So it's telling me that I have not installed the appropriate packages for ALE. I do have them installed. So let's try importing them. ALE.py. Let's try that. All right. So I have no errors now. Let's print out observation. And you can kind of build up over time what this does. So right now you have observation, and then we'll also print out, let's see, let's do obs.shape, if this has a shape. All right, so right now we have observation.shape. You can see it's 210 by 160.3, or by 3. We are going to go ahead and pass in a resize wrapper. Resize observation, env, and we want it to be 64 by 64. Now we have a 64 by 64 image. It's a much smaller block here of data. And it doesn't look like a smaller block because the print output is actually hiding some of it from us. But that's why we've got shape down here. So 64 by 64 by 3. And you'll notice the values here are 53, 95, and 24. Those are your color channels. If we then further say env equals grayscale observation, and we're going to say keep dim equals true. Now we have one column of data in a 64 by 64 image. So we're now just in a grayscale between 0 and 255. And what we've done here is without meaningfully decreasing the actual usefulness of the data, we have successfully simplified the data for the agent to learn. So that was our goal here, is anything you can do to simplify the data before it ever gets to the agent is better. It's going to learn much more quickly. It's going to be much more effective if you can simplify on the way in. All right, now I'm going to get rid of all this. We don't need it. We're going to go ahead and go ahead and declare our agent. We're going to pass in env, hidden layer equals hidden layer, learning rate equals learning rate, step repeat equals step repeat, and gamma equals gamma. All right, and we're going to run it, and no errors. And importantly, you'll notice down here we said loaded model on device CUDA 0. If you ran this and it said loaded model on device CPU, now is a really good time to pause the video and go try to figure out why that's happening. Why are you getting loaded on a CPU versus your GPU? Because if you continue on, the code will work, but it's going to run really, really slowly. So go ahead and figure that out. All right, let's go back to our agent.py over here. And now that we have a, this is something that's really, really important in a project. You know, you kind of saw me just code through a bunch of this without really running anything for the first probably hour of this video. That's not something you would really do in normal development. If I'm going to develop something from scratch, I'm going to get to a runnable thing as quickly as possible. Sometimes that's just running a Python file and getting a print statement. But I'm going to, build something that runs and does something useful, very, very quickly, so that I can start getting feedback and catch bugs and catch errors. When I coded out the first, version of this, I did not have it split into an agent class. I was just running a training loop right there in a main.py until I got the general idea of what I wanted to do, and then I started splitting it out into different classes. This is a good structure for you to have and work with, but if you're just starting to code something, you probably want to have the simplest possible structure that starts to get you some kind of results. So now that we've made it this far, we're going to be running the code much more frequently. And again, I'm using keyboard shortcuts. You can use that little run Python file. Should work just fine. That's going to have the same results. You can also, in my case, I've mapped in both the VS Code file and then also Control D, just because it's easy to reach to go and run this script. All right, let's go ahead and we've already set a to-do for process observation. We've loaded our model. Now we need to call our replay buffer. So self.memory is equal to replay buffer. This is the one we built earlier. I'm going to say max size is equal to 500,000. More is better. This works. I kept it smaller because I assume that you're not, maybe you're not running on a massive machine, but you can experiment with extending this and seeing how it changes the performance. So input shape is obs.shape. N actions is equal to env.action space.n, and device is self.device. All right, let's go ahead and just run this and make sure. And we messed something up. All right, what did I mess up? I've got n action and it needs to be n actions. Okay. Still didn't like it. Let's go see what, oh, you know what? We did not use n actions because it was unnecessary. So there is no n actions, I think. Let me look. Let's go look at our buffer. Yep. So we've got our input shape, our device, and our max size, and we do not have n actions. All right, so no errors that time. That's what we're looking for. Again, you should be running this as we go. Make sure it all works. If you have any errors, now is the time to stop and fix them. So we're going to do self.model equals model. Action dim is env.action space.n. Hidden dim is hidden layer. Observation shape is obs.shape. And we're going to say to self.device. And this .to is how you send something to the CPU or GPU. So remember, what we're basically doing here is saying to CUDA 0 to the GPU. All right. And then we're going to have a target model. And actually, you know what? I'm going to save myself some time and copy and paste. So again, your target model is going to lag just behind your main model, and that provides a certain degree of training stability. That's going to help stabilize your training and prevent wild swings. We're going to say self.targetModel.loadStateDict. So we're basically copying from the primary model at least to kick things off. All right, and then we're going to do self.optimizer is equal to optim.atom self.model.parameters. And we're going to pass in our learning rate. So the optimizer is going to be the thing that actually the algorithm that is used by your agent to go and actually attempt to update your model weights and learn whatever it's learning. Atom is considered one of the more advanced ones. Advanced in a good way, not advanced as in hard to use. It is a good starting place. You know, if you're not sure what optimizer you should use, just plug in Atom. It's probably the best for most use cases. When you get to a point where you have strong opinions on optimizers, then you know you can pick other options. But Atom is a really good place to start. And then we're going to say self.learning rate is equal to learning rate, just to set that. All right. Now we need our little helper function, our process observation helper. So we're going to do def process observation self obs, and we're going to do torch.tensor obs dtype is torch.float32 and permute 201. And what's going on here is the image returned by the environment is a very slightly different shape than what we need in our process. So we're just going to reshape it with that permute. So return OBS. Okay, and then up here we're just going to say OBS equals self.processObservation OBS. All right, and let's run it again. And you will notice that we are still, still functioning. And we have our convolutional output size is 1152, and everything is good. So now we get into the train method. All right, so down here, we are going to say def train. And that is also going to take a series of parameters. And if you're wondering why we don't just pass in all the parameters in the init method, the answer is you might want multiple training stages. You might want to experiment with different parameters. So we want the training stage to be a little bit more dynamic. So we're going to, this is going to be a bunch of params. It's going to be self, episodes, so how many times we want to run, max episode steps, summary writer suffix, batch size, how big of a batch do we want to train on, epsilon, epsilon decay, min epsilon. We'll get to what epsilon is in a moment. All right, and then what's our summary writer? And why do we pass in a summary writer suffix? So the summary writer is what we're going to use with TensorBoard. display data about the environment. So what we want to give this a name that both changes every single time we run. So we're going to put the data in it. But we also want it to be descriptive. So it should be something that tells us what was done in that training run. If we changed the learning rate and wanted to see how one learning rate compared to another, you might use learning rate in your summary writer so that you can see what that label is as you're looking at the data. So the way I've approached this is I have the summary writer name built up in here with the date, and then the summary writer suffix is something that the user can pass in the train.py. So let's go ahead and do summary writer name is equal to f runs datetime.now.strftime, and be very specific here. So it's going to be percent capital Y dash percent M dash percent D underscore percent H dash percent M dash percent S. And if all this is Greek to you, you can just look up time formatting syntax. Summary writer suffix. So we're giving everything a date. We're putting them all in runs. That'll create a runs folder. And then we are tacking on a suffix. And then finally, we can say writer is equal to summary writer name. All right. We're going to create the models directory if it doesn't exist. So if not os.path.exists models, then os.makeDirs models. We're going to say total steps is equal to 0. And then we're going to go ahead and start our training loop. So kind of coming back to our diagram, we have stood up our environment. We have an environment. We have a buffer. We have the framework for an agent. And we are starting to work on our training loop. Okay, so we've got our total steps. And we're going to say for episode in range episodes. And we're going to set up done equivalent to false. We're going to set our episode reward to 0. And then remember, we have to reset the environment. So we're going to do OBS observation info is self.env.reset. We're going to, again, call our process observation. If you're wondering why earlier we did, a process observation for a one-line change, it's because it's much more readable to say that, hey, anywhere we're calling an observation, we're just going to call process observation. And if we ever want to do additional observation processing, just tack it on in that function. Easy enough. Okay. Episode steps. We're going to start out at 0. And then episode start time, we're going to say time.time. We're just going to go ahead and capture our start time. All right. Finally, we are going to start the actual run. While not done and episode steps is less than max episode steps, we're going to start off by selecting an action. And this is where epsilon comes in. So we are using what is considered an epsilon greedy policy to select actions. So it's going to, when we start off, epsilon is going to be high. Epsilon is going to be 1. And what that's basically going to mean is that all actions are random. So, we right off at the beginning of the process, our agent isn't going to know what actions to take. We need to generate some kind of data for it so it can start learning. So an epsilon greedy action selection is that it starts out, that's greedy in respect to epsilon. It's going to start out taking random actions, and then as epsilon shrinks, That's what our epsilon decay variable is going to be. So as epsilon shrinks, it is going to take actions based on our policy. So, when epsilon is 1, it's going to take all random actions. When epsilon is 0.5, it's going to take 50% random actions and 50% actions based on our learned policy. When epsilon is 0.1, which is where we're going to stop it, we're always going to keep some randomness. So when epsilon is 0.1, then it's going to take 90% actions based on the policy and 10% actions based on randomness. So let's go ahead and code that in. We're going to do if random.random. That's going to be a random value between 0 and 1 is less than epsilon. Then action equals self.env.action space.sample. Else, we're going to collect Q values. Remember, Q values are the value of a state in an action, or in this case, it's going to return the values of all states with a given action. We're going to say self.model.forward, and we're going to unsqueeze the observation along the 0th index and send it to self.device, and then return index 0 from that. So we're sending this to self.device because everything that's on the GPU must be sent to the GPU before it can be used there. So I think I said that strangely, but what I mean there is because the model is on the GPU, if you do not send the observation to the GPU first, it's going to give you an error saying that, hey, found tensors on 2 different devices, and it's going to kick it out. All right, and then we're going to say action is torch.argmax, Q values, dim is equal to -1, dot item. And what this is basically going to do is it's going to take, this will return, the values of various actions. This is going to select the index of the highest value action. So if this returns a probability distribution saying that action 2 is a 0.7 probability of success and action 1 is a 0.3 probability of success, this torch.argmax is going to actually return a 2 that we can then pass into the environment. This is something that will change based on the type of environment, if it's continuous, if it's if there are depending on the type of input you want, you will need to tweak this section and quite a bit of other things too, but that's an area to focus on. We're going to go ahead and set reward to 0. And now we get into the repeat. Well, and you've seen me type in the step repeat several times, and I haven't really explained what it is. So now we're gonna talk about that. So every single frame is a step in this agent's world. So if you think about it, you might be playing a game at 60 FPS, but you're probably not acting every single frame. You're not acting 60 times a second, because not that much changes from second to second. Maybe you're acting every 10 seconds or every 30 seconds. The agent is taking a step every single frame. We want to back that off a little bit. We basically want to say that, hey, you should just take the same step, the same action for a certain number of frames before trying to get a new observation, because there's very little chance that anything's changed between step 1 and step 2, but maybe something will have changed between step 1 and step 4. So what we're going to do here is say for I in range, self.stepRepeat, reward temp is 0. So we have to collect the reward each time. Otherwise, that could end up getting lost. We're going to say next OBS reward temp, done, truncated info, self.env.step, and we won't actually use truncated or info, but we do have to collect them, equals action. And then we're going to say reward plus equals reward temp. If done, so if one of those actions got us to done, go ahead and break. All right. We will then say next obs is equal to self.processObservation. Next obs, we'll go ahead and process our observation. And you can do something called you can do another environment wrapper. That's an option for you to dig into. So, we imported gymnasium wrappers for grayscale observation and resize observation. You could actually import you could create your own wrapper to, basically do what we're doing in process observation. With this being an attempt at a beginner series, I didn't want to go down the self-creating wrapper route. That did not feel like something that was very beginner friendly. So that's something for you to dig into, is you could just have your own wrapper and not call process observation, each time. All right, now we get to self.memory.store transition, OBS, action, reward, next observation, and done. Okay. And going back to our diagram, we just did this portion. So we now have our agent that is feeding data into the buffer. All right. Now that we've stored observation, action, reward, and next observation, we need to go ahead and set OBS to next OBS for the next loop. We can go ahead and add episode reward, or add reward to episode reward. We can do episode steps plus equals 1. So we're adding up the rewards, we're adding to the steps, we're adding to total steps. We're basically incrementing all of our metrics. All right, now we are going to get into the actual training loop here. And this is a little bit complex, but let's plow forward and see what we can do. So if self.memory.canSample, in other words, if there's enough data to pull a batch of batch size with our batch time size times 5 limit in place, then we're going to pull observations, actions, rewards, next observations, and dones from self.memory.sampleBuffer batch size. And if you're wondering why I did not abbreviate OBS here, I felt like by the time we get into plural, obses just sounds harder to deal with than observations and next observations. So we're sampling our buffer. Again, if we come over to buffer.py, that's basically exactly what we just said here. States, actions, rewards, next states, dones. Observations, actions, rewards, next observations, dones. Make sure these line up. I have absolutely run into bugs where maybe I was pulling back observations as next observations, or, swapping out actions and rewards. Check, make sure all this lines up. All right, we're going to do dones is dones.unsqueeze, and unsqueeze is just going to add an extra dimension, .float. We are going to get our current Q models, or current Q values from both models. So we're going to say Q values is equal to self.model observations. So up above, we were calling the model to get an action. Now we're calling the models to actually train the models. So we're going to say actions equals actions.unsqueeze. 1.long. QSA batch. That's Q value, state value, action, or Q of, the Q value of state and action batch. That's what QSA stands for here. We're going to say Q values dot gather one actions. So basically, we're going to gather the Q values of the actions that were taken, or the, that's what we're saying. So we're going to gather the values of the actions that are actually in our batch that the agent took. Now we're going to grab next actions, torch.argmax for self.model. So now we're looking at predicted next actions based on next observations. Keep dim equals true. And I'm going to come back to our diagram one more time. So what are we doing here? Next actions, predicted, why are we grabbing the next actions based on a predicted value? Well, when we came down here in our table, none of these are real values. The 6, the 7, the 8, the only real reward in this table was 10. So what we're doing is we're predicting that this has a value of 6 based on the predicted value of 7 here. We're predicting that this has a value of 7 based on the predicted value of 8. So what it's trying to do is it's trying to get the predicted value of future rewards and feed those back into the current state and the actions that it can take in the current state to maximize those rewards. So that's why we are doing next action prediction. And if this is all really confusing, it is the first time. This is one of those places where you want to read a lot of code, write a lot of code, spend a lot of time with it, and it is going to get a lot more comfortable over time. I think I probably went through 4 or 5 of these before I really got what was going on and it clicked for me. Maybe you're faster than me. You might be, but don't be surprised if it takes a little bit of time to really have some of these things sink in. So we're going to go ahead and say next Q values is equal to self.targetModel next observations dot gather one next actions. We're going to grab a target batch of rewards dot unsqueeze 1 plus 1 minus dones times self.gamma times next Q values. All right, so I want you to build up a really good intuitive understanding of what's going on here. So our target batch, we're grabbing the current rewards, the real rewards received in a step. We are adding, 1 minus dones. So dones in this case, if done is a 1. So basically, if done is 1, in other words, if the match is complete, then this is going to come back as a 0, and it's going to zero out the whole side of this equation. Gamma is your discount factor. So we passed in a gamma of 0.99, and your discount factor is how much we value future rewards. So you don't want to value future rewards as much as present rewards. Otherwise, why would it ever go for present rewards? It'll just try to maximize future. You want to value them very close though. So what this is doing is it's saying whatever the predicted next Q value. So going back to our, drawing here, it's basically saying, I'm going to try to get both of these up at the same time. There we go. So if next Q value is 10, then it's going to multiply that by self.gamma and get a value of 9.9 something. So we're trying to predict the target, right? So if next Q value is 10, self.gamma is going to get us to 9.9 something. Assuming the match isn't done, it's then going to add that to rewards. So it's going to try to stack up all of the future reward values and represent that as the value of the current state. That's what's going on here. All right, we're going to do loss is equal to f.msc loss, and that's going to be QSA batch and target batch.detach. And the loss is how you calculate, whether the agent's going in the right direction. MSE is mean squared error. So what it's going to do is it's going to take the difference between QSA batch and target batch, and it's going to take the mean, the average of those two things, and then it's going to square it. So make it, larger by a square value. So that's what MSE loss is doing. Difference between the two, square them, or take the mean, square them, you have MSE loss. And the squaring also makes sure that it's never negative. All right, we're going to go ahead and graph our loss. So this is where our writer finally comes in. So we're going to say writer.add scalar loss/model loss.item, and we're going to graph total steps. So this is the label, the thing you're graphing, and then or the y-axis of your graph, and then this is your graph's x-axis. If you didn't pass in your steps or you made this a static value, you would just have a point on the graph, and it would never move to the side. It would just move up or down, and that wouldn't be very useful to you. All right, now we do the backprop. So backpropagation is where we're actually going to take the loss and we're going to go backwards and adjust the model based on the loss value. So self.model.0grad loss.backward and self.optimizer.step. And then finally, we will do our soft update. So if episode steps percent, so modulo 4 is equal to 0. So in other words, every 4 steps, we're going to do a soft update of self.targetModel and self.model. All right, and then go ahead and enter in a couple of times, go two tabs to the left, and we are going to basically every episode, we are going to save the model, which again is easy because we built that functionality into our model itself. And then finally, we're going to do writer.add scalar. We're going to go ahead and capture our score, episode reward, and episode. We're going to do writer.add scalar epsilon. And that's just so we can see, the effect that epsilon has on training. We're gonna track it as it goes down. We're going to say if epsilon is greater than min epsilon, we'll do epsilon times epsilon decay times equals. There we go. And then we will finally capture our episode time is going to be equal to time.time. So current time minus episode start time. And this is just useful data to see how quickly things are moving. And then finally, we will print out some completed episode, and we'll have our graphs, but I also like to have some text output with specifics with score episode reward, print f episode time will be episode time 1f seconds, print f episode steps, episode steps. All right, and that is the end of the train function. I know that was a bit of a slog. That was a long one. Hopefully all of it works. Let's go ahead and go back over to train.py, and we are going to need to define a few more variables up here. So we're going to say episodes is equal to 10,000. Max episode steps. I would make this, some arbitrarily large number is equal to, let's do 5. We'll do 10,000. Why not? Total steps. Let's see. Do I even use total steps? Hang on a moment. I don't think I do. All right. We already did step repeat. Let's come down here, just come down to the end, and we are going to do batch size. We're going to do a batch size of 64. We are going to do an epsilon of 1, min epsilon of 0.1. And by the way, if you're wondering why I'm using epsilon instead of something like, a more descriptive variable, percentage of randomness or something like that, epsilon is what's used in most of the papers for this. You might as well get used to that being what it's called. Yes, it's confusing when you're first looking at this to hear gamma and epsilon, and but that is kind of what these things are commonly called. So, go ahead and dive in. We're going to do epsilon decay is equal to 0.995. You can play with this value. And I think we got everything else. So with that in mind, we need to set a couple of additional variables here. So we need our summary writer suffix. And you can make this whatever you want. This is your label. I'll show you what I did. So DQN, LR equals learning rate, because that's something I might want to see in the label. HL equals hidden layer. BS equals batch size. And that should do it. And in general, if you're going to tweak a variable, like, hey, you wanted to tweak step repeat, I'd probably come add step repeat to this, because what you're really using this for is being able to see what parameters you ran this with at different times. And then finally, we can go ahead and run agent.train. Episodes equals episodes. Max episode steps equals max episode steps. Summary writer suffix equals summary writer suffix. Batch size is equal to batch size. Epsilon, not episodes. Epsilon equals epsilon. And epsilon decay is equal to epsilon decay. And then min epsilon is min epsilon. All right, moment of truth. Let's see if our training kicks off. And it does not. We immediately ran into a problem with reward memory. So let's come over here and let's see what this should have been. We hit a data type that we weren't ready for. So reward memory should be torch.float32. Basically what this is telling us is we tried to pass in a -1, and you can't pass a -1 into, okay, what don't you like? Python terminal views cannot interpret torch self.float32 as a data type. Well, it should be able to. All right, I was looking at the wrong section of my other code. It is going to be np.float32. Let's try it now. All right, missing one required positional argument. This is the fun part, the getting it working after it's all there. L1 loss forward call. So let's scroll up. And by the way, when you hit errors like this, I'm going to encourage you to resist the urge to go punch it into ChatGPT or another LLM. Read through it, try to understand it, try to fix whatever's wrong without going down the LLM route, and you will learn much more quickly. All right, so it doesn't like, we're in x.relu of self.fc3. If we go look at model, which is interesting, so that means we got down to here before, although that's in L1 loss forward. So is that really where we are? We're in self model observations, line 107 in train. Okay. Okay. So we should be pulling back observations from sample buffer. All right, so I found it, and maybe you caught it earlier. But if we look at my definition here, I let some autofill happen. I let my IDE autofill L1 loss instead of nn.linear. So let's save that and try one more time. All right, and we are now up and training, which is awesome. This is really good progress. We are almost at the end. This is going to run for a long time, a very long time. So let's go ahead and move over and start working on our test script and our test method. So in agent, just let it run, let it do its thing in the background. So in agent, we're going to do def test, and test is only going to take self. We're going to do self.model.load the model. We're going to do OBS info is equal to self.env.reset. And then really, let's see how much of this we can just borrow. So total steps, done equals false, all that fun stuff. Let's go ahead and come down and grab all of this and copy it and paste, because I think a lot of this is going to be really useful. Now we don't need that. Go ahead and tab it over, because we're not going to do multiple episodes. We don't really care about episode reward. All we're trying to do here, let's go ahead and we're just going to hard code this to 0.05. And we're just going to say while not done. Okay. Let's see if we even need, we don't care about episode steps. We don't care about episode start time. Because again, this whole section is just to watch the model run, to be able to see what's going on. All right, so while not done, if random.random, yep, go ahead and pull Q values. Reward equals 0 for I in range. Self.step repeat, that's all fine. And then we're just going to do OBS equals next OBS down here. And that is probably a good place, or no, OBS equals, hang on, I was about to miss our self.process observation. Next OBS and episode. And then we probably do want episode reward. I'm not going to do anything with it right now, but you can print that out if you're interested in it. So we'll go ahead and do plus equals, yep, reward. All right. And then let's go play, and we'll add a little bit more to this in a minute, but I want to show you why we need to add more to it. So test.py, we are going to be able to grab some of these. So you won't need all these parameters, but it also won't hurt anything to have them. So let's just go ahead and copy over everything except for the train call. And yes, this is code duplication. Yes, you should try to, the dry principle, don't repeat yourself, tells me don't duplicate code. But in this case, it's two different inputs and I want to be able to test and play with it as I build. So we're going to start with a render mode of human, and I want to show you the problem with that. So the default way that, that Gym makes an environment available is by saying render mode human. So we are going to leave that, and we're going to call our agent. We really don't need summary writer prefix anymore. So we're going to call agent.test and just see what happens if we got everything right. So what we should get, if we made no errors, is we should get Pong. And this is our agent playing. And you can see it's really, really bad right now. It's not going anywhere. Ours is the green, by the way. The orange is the default computer, and it's just scoring over and over again. So we have a very dysfunctional agent at this point. But this is huge. Like, I can't see the bottom of the screen. It makes it really hard to see. I mean, obviously you can see the score, but it makes it really hard to see how well our agent is doing. This does not provide a default way to actually, resize this screen. You'll notice I can't click on it. If I right click, I don't have a resize. It's huge. So if that is not a problem for you, then you're actually done. You can just leave this alone. You can change nothing. You're fine. If you have the same supersized problem that I have, then let's go ahead and go fix it. So again, there's no resize option. So we are going to code our own resize effectively. And we're going to do this with CV2. So we're going to come in here and we are going to say, we're going to go back to test.py, and we're actually going to change this back to RGB array. We cannot leave it in human. And we're going to say frame is, we're basically going to go grab a frame. So we're going to grab it from self.env.env.env.render. Now, why are we calling env.env.env? That looks really weird, right? Well, every time you call a wrapper, So if we come back here, we're wrapping it in resize observation and grayscale observation. So if I just call self.env, I'm going to get grayscale. If I call self.env.env, I'm going to get the resized observation. So this is small and gray. This is small and colorful. This one is going to be the full-sized image that we can then take and do things with. And that's what we actually want. So we're going up a couple of layers here in our environment stack. We're going to say resized frame is equal to CB2, which is an image processing library, dot resize frame. And I'm going to say 500 by 400, just because that's the size that worked for me. We are going to say resized frame equals cb2.cbt color, resized frame cb2.color RGB to BGR. And we're doing this because Gym outputs a different color profile than CB2 expects. And then we're just going to do cb2.imshow Pong AI resized frame. And then if we're going to go ahead and set it up so that we can hit quit to exit if we want to. So if cb2.waitKey 1 and equal to ord Q, then break. And then finally, actually, let me just show you what it does. And then you can see why we're going to add a sleep. So we're running it, and hey, it's working, but it's also incredibly fast. So because you just saw it at the speed the agent is playing it and can display, which is not a very human-friendly speed. So I'm just going to put a time.sleep 0.05 in here. And we are going to run this test.py. And now it's a little bit more of a human-friendly speed. And you could obviously tweak that up or down depending on how fast you want it to be, but that's about where we landed for me. All right, let's go ahead. So right now, obviously, the agent isn't doing terribly well. Let's go ahead and launch TensorBoard. So we did some work for observability. Let's go see our observability. So in VS Code, Control-Shift-P gets you the command interpreter, and then you will go to launch TensorBoard. It may not be at the top for you. You might have to type Python:/launch space TensorBoard, but then after you do it the first time, it will be at the top. This will basically sort all of the things that you've done in VS Code recently by most recent usage. I always get this little error. If I click yes, it never actually works. So I click no, click use current working directory. And my preferred view over here is scalars. So this is all the runs, and you'll notice these are the 2 failed runs. So I'm just going to uncheck these because they're not useful. And then what you can do here, go over to score and then smooth out your score. So this is your smoothing. So we want to see what direction it's going in. And you can see we've kind of bumped along up to the 400 mark. Now, this is also why, though, we're charting epsilon. Because you could guess here that we're not learning anything, because that does not look like a very happy learning curve, right? Except we've been losing randomness this entire time. So we've just gotten at the 450 episode range to the point where we are no longer just pure random. And honestly, it's pretty normal as your agent takes over from randomness for it to show worse performance. So I'm going to pause the video here and let it run. If you have followed me this far, you're probably in a good place to just wait. It's going to take a successful run. So let me pull up my other, because this is one where I have done this before. Here's my other code base and my last run, and you can see kind of what the performance did here. So we did have around the 500 mark, we were already trending upwards. So that tells me that something is probably a little bit off here, and we're not quite where we need to be. So let's dig in. So we're not learning. We have a previous run where we know we should be learning. I'm going to pause and look at this. All right, so I found our bug. If we come over here to, and I did already fix it, but I can show you what that was here in the Git diff. So you'll notice here, originally it was next states equals self.state memory, and that should have been next state memory. So found the bug, went and retrained. This is about an hour in the future. And you can see here, our agent is on a nice upward climb here. My experience is that this will continue improving for quite some time. But let's go ahead and test it and see where it is. And I will probably wrap up the video and leave further training as an exercise for you. So you can see here, our agent is playing successfully. It's not superhuman. It's still missing some scores, but it is playing, like someone who understands the game and is, capable of taking actions on it. So yeah, I think all in all, we have been successful again in only about 500-600 iterations so far. We have a Pong playing AI that's capable of at least, matching, going toe to toe with the default computer generated player. So let's talk about next steps. I recommend going and taking the code that we've just built and applying it to different environments, using it for other things. It's, the real learning happens when you try to stretch outside of what's in the tutorials. So, this has been a code walkthrough. Hopefully you've sat and you've coded it all along with me, and you've learned something from the process. You're going to learn a lot more the first time you try to take it and apply it to something other than Pong and find out that it does or doesn't work and dig into why and fix those places where, you find breaks. You're going to learn even more when you sit down and take a different algorithm and try to build it out. I recently launched a blog, and I am going to link an article that I put out there for my recommended path to get into reinforcement learning. So I've got a few different courses and authors that I recommend, and I will put that in the video description. There's also, for those of you who are interested, there's a Bot Lab Discord in the video description that you're welcome to join to come, hang out and talk about these projects and robots and RL and other fun things. And then, of course, I will post all of the links that we talked about in the beginning of this series or this video, as well as a link to the completed code on GitHub down in the video description. So all the goodies, scroll down, take a look. If you've liked what I've put out here, if you enjoy talking about reinforcement learning or robotics or AI in general, do me a favor, hit like, hit subscribe. I'm going to continue posting this kind of content. This is an area I find incredibly fun. I am not a professional in this space. I am a fan of AI and a very enthusiastic hobbyist. So come hang out with me. Let's build some more cool stuff. And with that, I will say until next time.